Hello friends, welcome back. In this video, we will discuss about Virtual Port Channel or VPC, which is the flavor of multi-chassis link aggregation that runs on Cisco Nexus platform. But before we discuss Virtual Port Channel, we will quickly have a discussion on multi-chassis link aggregation or MLAG in general. So speaking about a common network architecture where we have the three-layer design, that is the core, distribution, and access layer, we generally have the access layer as a single point of failure from both the link and the node's perspective. We can add redundancy to the platform by adding redundant power supplies, additional NIC cards to the servers, and additional links from the switch to the end server. But layer 2 multipathing from a spanning tree point of view is not supported, which eventually results in wasted links, wasted bandwidth, which ultimately results in wasted capital expenditure. So how do we avoid wasted links in our network? So the solution is to trick the end server into load balancing the traffic between the uplinks. So with multi-chassis link aggregation or MLAG, we now have the feature where we can spoof the end server into believing that the uplink switches are one device instead of two devices. So like we see on the screen, with STP, we had the problem of wasted links as we see on the screen. But with VPC, the endpoint server, again, it doesn't have to be a server, which could be physical server, firewall, a load balancer, any device at the service layer. We could spoof that endpoint device into believing that these two physical boxes are one logical unit. So with multi-chassis link aggregation, physical triangle appears to be a logical point-to-point port channel between the Nexus devices and the endpoint device. So from the endpoint's perspective, we configure a NIC teaming or some sort of link aggregation on the endpoint device. And on the uplink switches, we need to have some sort of a mechanism to synchronize the MAC address table, the ARP entries between those devices for load balancing and ensure that there are no loops in the network. So like we discussed with MLAG, we form a physical triangle between the access switches and the endpoint device. However, from a logical topology perspective, this appears to be a point-to-point link or point-to-point connection. The benefit of this design is that apart from adding redundancy to this topology, both in terms of link level redundancy or node level redundancy, we also add additional bandwidth to the endpoint device. So now for the endpoint device, we have two links to its upstream device, and it can be used in an active-active manner. Now, the challenge with this topology is that the participating switches need to have some sort of mechanism to synchronize the control plane information between them so that both have the same copy of the MAC address table and ARP cache if they are doing layer 3 forwarding. So how this control plane information gets synchronized between the participating switches depends on the specific flavor of the MLAG or multi-chassis link aggregation protocol running on that particular hardware platform. Also, as we are spoofing the endpoint device into believing that the upstream switches are one logical unit as compared to two physical units, this topology breaks the traditional loop prevention mechanism of spanning tree. So we need some new loop prevention rules to avoid broadcast or unknown flooding storms in the network, with the final result being that active-active layer 2 forwarding is now supported in the network. So friends, let's have a quick discussion about the other MLAG implementations supported on some of the other Cisco platforms. So we have Catalyst Virtual Switching System, or VSS as it's commonly known, and that is supported on Catalyst 4Ks, 6500, etc. And then we have the Catalyst Cross Stack Ether channel supported on 3750, 3850 stack switches. And more recently, we've had the Nexus Virtual Port Channel, or VPC, supported on Nexus 5K, 7K, 9K, etc. And like discussed previously, the goal is to have multiple physical switches that are configured to appear as a single logical chassis, and we synchronize the control plane between the two of these switches. So from a physical wiring point of view, we have all of these three devices look as a physical triangle, but logically they appear as a point-to-point connection. Also, the main difference between stack-wise versus VSS versus VPC is that Catalyst Stackwise and VSS use a single control and management plane, which means that the switch pair has a single management IP overall, and the switches share the same control plane. So from a configuration perspective, we log into the switch pair using a single management IP, and once logged in, the switches appear as modules in a modular switch platform, and the synchronization between the switches takes place via the virtual switch link or VSL, whereas in the case of Nexus VPC, we use two separate control and management planes, which means behind the scene we run multiple copies of the control plane instances like STP, BGP, FHRP, IGP, etc. And in the case of VPC, the synchronization takes place via the VPC peer link, which synchronizes the MAC address table, the ARP cache, IGMP snooping cache for layer 2 multicast to make sure that the forwarding in the data plane is equal between the two peers to avoid traffic loops or black holing. But we will discuss the VPC peer link and the keep alive mechanism in the upcoming sections, along with the Wireshark packet captures like we usually do in this channel. So friends, let's have a quick discussion about the high-level components running on the pair of Nexus switches configured to run VPC. So VPC consists of two physical switches called the VPC peers. There is a consistency check that runs behind the scenes over a control plane protocol called the Cisco Fabric Services over Ethernet or CFSoE. And this protocol synchronizes the control plane information like the MAC address table, the ARP cache between the pair of VPC peers. And this CFSoE protocol runs over the VPC peer link, which we configure at the point of establishing the VPC peering. And when the peering is first established, they will exchange their physical parameters like the model number, the version of NXOS running on them, the line card installed. This is to ensure that the two switches are physically compatible with each other. And from a configuration point of view, we configure the VPC peers with a VPC domain ID, and this VPC domain ID is shared between the VPC peers. And based on this domain ID, the VPC peers generate a link aggregation control protocol system ID or lag ID, and it is this lag ID which is used to spoof the end server or the endpoint device to believe that it is connected to the same access switch upstream instead of two separate physical switches. So friends, in our next section, we will discuss about the VPC configuration, specifically in terms of configuring the peer keep alive, peer link, and the VPC member ports, and also the order in which these need to be configured, as VPC is very sensitive to the order of operation, and we will go over the VPC workflow in a detailed manner using a lab scenario. So please do join me in the next section where we'll discuss the implementation and verification of VPC peering on a pair of Cisco Nexus switches, along with the Wireshark captures. I hope you like this overview of VPC on Nexus platform. And if you did like this content, please hit the like button, share the video as much as you can, and any comment, good or bad, is welcomed. And if you haven't subscribed to my channel yet, please hit the subscribe button, and I will see you all in the next video. Thank you very much for stopping by today. Thank you.